So we're going to take a look at the function f of theta. Let's use a new variable for change. Is the sine of theta over theta. And we looked at this numerically in a table. We looked at it graphically on the computer last week sometime. So we're going to look at it geometrically and algebraically today. So I want to know for this function, what is the limit as x goes to 0 of the sine of theta, oops, theta, not x, over theta. What is this thing? Now, if I try to apply the quotient rule here, the quotient rule says, yeah, you can use it as long as the limits exist and the denominator is not 0, but the denominator is clearly 0 here, so the limit laws do not apply. So I got to try something else. So we're going to go back to the origins of the sine function here and consider the unit circle. That's my best unit circle today. Here's the y-axis, the x-axis there. So that's the point 0, 1. Up here is the point 1, 0. Oh, I got those backwards, didn't I? 1, 0, and 0, 1. My y-axis is here, my x-axis is there, and if I pick some point, and let's stick with the first quadrant for a moment, so that's my point right there, and I connect a line segment from the origin, then this angle right there is my angle theta. If I drop a perpendicular from that point to the axis here, so that right there is a right angle, then this blue line right here is the sine of theta, right? So I have a version of theta here, I have the sine of theta here, and hopefully you remember from your trigonometry days that this arc right here on the unit circle is also theta. Okay. If we scale the circle up by r, then the arc length is r times theta. So theta is the angle, theta is also the arc length on the unit circle. Another interesting fact here, if we extend this, let's see, am I on red? If we extend this segment here out a bit farther, let's make it kind of a ray there. And then I draw a perpendicular from the point 1, 0 up to that line. Does anybody know what that length right there is? Let's erase that theta for a minute. Put it in here. What is this length right there? Let's see, nothing in the Zoom, the chat at the moment. Hopefully your brains are thinking. What is that right there? So just a side note about that. We have two similar triangles here. We have the inner triangle at that angle theta and the right angle. And let's draw the blue one here, the bigger one. Oops, I was supposed to make that blue. Here's the outer one there. And this is the one I'm trying to figure out. What is that right there? That's the same theta. That's the same right angle. So these triangles are the same shape. So this one right here has the sine of theta for that one. There's a 1 right there, and the cosine of theta lives here. And so if I use ideas of similar triangles and I want to identify that right there, what I can do is say, well, I know this side right here is a 1, right? Because distance from here to here is 1. Question mark, right? That opposite side of the angle over 1, the adjacent side on this triangle has to be equal to the opposite side of the smaller triangle divided by its adjacent side. And is there another name for sine over cosine that uses a little less ink? Anybody there? Tangent. Thank you so much, Abigail. Appreciate your contribution. Yeah, that is the tangent of theta. So on this picture right here, this other line is the tangent of theta. Some things to consider here, that this arc right here is always going to be greater than the sine of theta there. Okay, so I've got the sine of theta is going to be less than or equal to theta. If theta goes to 0, they're both going to be 0, so they are going to be equal to here. If I divide the theta on both sides, because I'm not actually getting to 0 in the limit, I can divide by theta, that's okay, then I get the sine of theta over theta is going to be less than or equal to 1. Okay. So that's kind of an important thing. But what we're going to do next is we're going to apply a thing called the squeeze theorem here. And what the squeeze theorem says is if you have some functions like f of x and g of x, and let's say we have a third one called h of x, and they all sit in this hierarchy here where for any x value, h of x is bigger, g of x is in the middle, and f of x is smaller. If we take limits as x is going to some number for each of these, a side note, and we'll apply this in a second. If the limit of f of x exists, and let's say it's equal to L, and the limit of h of x exists, and it is also equal to L, then we've trapped g of x in between. And so then the limit of g of x is also going to have to be L because it's stuck in between there. So this is called the squeeze theorem. So we're going to apply it to this situation. And let's see, I'm running out of room here. So I guess I'll have to redraw this on the next page. So if I just take a look at that first quadrant here, where I have my quarter circle there, and then I have my ray heading out here for theta, and then I have the sine there, and the tangent here, then the three things of interest to me to set up this squeeze theorem is that inside that red line is the sine of theta. This blue arc in the middle is theta. Oops, that was supposed to be blue. Try again. There we go. That's theta, the arc length. And then out here, this green length is the tangent of theta. And so from this geometry, we end up with that the sine of theta is smaller than or equal to theta, which is smaller than or equal to the tangent of theta. So here's the inequality I get from that picture. Now I'm going to apply a bit of algebra to this. So the first thing I'm going to do is I'm just going to divide the sine out. So I'm going to divide everything by the sine of theta. So when I do that, well, sine divided by sine is 1. So I get a 1 there. I get theta over the sine of theta, which is the reciprocal of what I'm interested in. We'll fix that in a minute. And over here, tangent is sine over cosine. And so the sines are going to divide out, and that's just going to leave me 1 over cosine. Now I can flip this by reciprocating each fraction and then turn it around. So if I reciprocate 1, I still get 1. And then less than or equal to the sine of theta over theta. Oops, when we flip it, we reverse the inequalities too. So that becomes sine theta over theta, and then this becomes 1 over cosine of theta. And then we're going to reverse it again. So rewriting it so the inequalities are facing this way, then the 1 over cosine ends up over here, 1 goes there, and the sine of theta is in the middle. So now I've done a little algebra, I've got the thing I'm interested in, I can apply limits. So I can rewrite this by saying, hey, let's take the limit of everything here as theta goes to 0. So the easiest one to resolve here first is, well, as theta goes to 0 of 1, who cares what theta is doing? 1 is 1. So I get a 1 right there. Over here, I can take the limit of the quotient if they exist. Well, the numerator clearly exists as 1. Then the question is, well, what is the cosine of 0? Anybody? Cosine of 0 is cosine of 0. It's one I'd hoped you had memorized from your trigonometry days. What happens if we plug in 0 to cosine? Thank you, Kelsey. We get 1. 1 over 1 is 1. So what I now have is the limit that I'm interested in is trapped between 1 and 1. So the limit as theta goes to 0 of the sine of theta over theta has to be 1. It's got no choice. It's squeezed in there. So again, what's the point here? Well, limits are complicated some of the time. And so far, the biggest thing we've come across that's trouble is 0 over 0 requires a great deal of work. So we've looked at some algebraic tricks, some graphical tricks, and some numerical tricks so far. We'll continue to play with that. Probably got a couple more problems to do tomorrow related to this, but you should be finishing up the homework for 2.2 and starting the homework for 2.3 today. That is it for now from the calculus workshop here at BMCC.